Hello, everyone, and welcome to today's webinar, What's New in Kubernetes? Before we get started, I want to explain how you can participate. For this webinar, you have automatically joined the audio through your computer speaker system or the mobile app. Please make sure your speaker volume is turned up. If you have any questions during the presentation, please enter them into the questions panel and one of our Docker experts will respond. We will also take questions at the end of the presentation. Please know this session is being recorded and you will receive a copy of the recording via email in a few days. I would now like to introduce our speaker for today, Keith Hutchins, Docker Technical Alliances. I will now turn things over to you, Keith.
Hi, everyone. My name is Keith Hutchins. I work in the Technical Alliances group at Docker. My primary responsibility is working with our technical partners, particularly in the area of storage. I'm responsible for the Docker certification testing for all of our storage partners and storage requirements. And I thought it'd be a really good idea to talk to you guys about databases and how you can run them in production in your own deployments. So let's get started. First of all, let's talk about storage and how containers work when it comes to storage. So we all know that container images are stateless, right? When you stop a container, any changes that you make to the container itself, any files that you write inside the container, they disappear, they're gone. Docker will actually throw the entire container image away as soon as you stop. It's part of the copy on write system, how we maintain diff layers in containers at runtime. However, the containers themselves don't have to be stateless. The container is, but you can attach a separate storage volume to that container. With standard Docker and Docker Swarm, we have a Docker volume create command. What that does is it basically takes a directory on your Docker host and bind mounts it into the container at runtime. So just like mounting any other volume into a standard Linux system or a volume into a drive letter on Windows, it works exactly the same way. That volume has a totally separate life cycle from the container. So when you shut down the container, the volume is still floating around. It's either, again, a directory on the host, or if you're using external systems, which in production you should be, it can be iSCSI, NFS, pluggable storage for a cloud, or any of dozens of third-party drivers that we have certified for Docker, and we'll talk more about that a little bit later. So this is how you achieve persistence with your containers. You store your data in that volume. Just have your the software that you're running in the container configured to store stuff in that particular directory that you know where you're going to be bind mounting it into, and then you're off to the races. So that being said, persistent storage in Kubernetes works the exact same way, only it's a little bit more involved. You don't just say at the command line Docker volume create and then attach that volume to a container at runtime. You actually have to prepare things a little bit more in advance. So Kubernetes storage is operator driven, and what I mean by that is that the operators of your Kubernetes system will have to create a storage class. And I'll show you an example of a storage class as we get started with the demo part. But basically what it is your system administrator creating a storage pool available for your applications to use. Typically they'll make one of them a default storage class, and then but if you have multiples, you can set up several different storage classes that are available for use. Under the hood in Kubernetes, you can either provision a big pool of storage. Basically, you configure the storage class to talk to a driver that reaches out to an external system and can carve out storage and mount it at will. Or you can actually pre-configure volumes. So you literally have a pool of predefined volumes that can be used and reused. Talk to your sysadmins for setting that up if you want to do things that way. Typically, you'll use dynamic provisioning for that. So when Kubernetes users want to use storage, they will create a thing called a persistent volume claim. And this is basically just this is essentially kind of an order ticket that you'll create. You can create them in YAML, and Kubernetes will return a persistent volume. So basically a persistent volume claim is a request to Kubernetes. Kube will then issue a persistent volume that's bound and attached to that PVC, and then you can use the PVC in your application definitions later on to be able to attach that volume. And remember, the persistent volume claim is separate in the lifecycle from the actual containers of the Kubernetes pod. So let's a little diagram show you how the workflow happens with this. So we've got various and sundry storage devices, whatever it might be, network attached, storage attached, block volumes at a cloud, doesn't really matter. Those are connected through an integration API into Docker and Kubernetes. The integration APIs for Kubernetes, Docker supports in the upcoming Docker Enterprise 3 release. We support almost all of the major storage interfaces for Kubernetes, and that means that the Kubernetes entry storage drivers, we will support quite a few of those. They all will work. Some of them we directly support. A lot of them are written by third-party drivers, by third-party authors to support their particular storage. As an example, NetApp has the NetApp Trident drivers. Those are separate from the Docker drivers, and they are supported by NetApp, and they're good partners of ours. The container storage interface as well, CSI, is fully supported by Docker Enterprise 3. We just don't support the flex volume interface, at least not yet. So moving forward, once this integration is done by the Kubernetes sysadmins and your deployment, then they will define the storage class. And then the life cycle is, again, you create a persistent volume claim, which goes back to Kubernetes. And so in the PVC, you define which storage class you want to use. The Kubernetes returns a persistent volume attached to that PVC, and then you can bind that persistent volume claim to a pod with containers running inside. That's basically the workflow for that. So a couple of notes for it. When you're talking about databases, it's a little bit harder to work with, particularly for old school databases, databases that were basically written and coded before dynamic infrastructure, like infrastructure clouds, such clouds like Amazon Web Services or Azure, things like that. Basically, the architecture of these databases is defined in ways that you put a database on a physical server, and if that server goes down for whatever reason, you have to have backup copies and backup running copies of your databases to make sure that things stay up and running. You cannot instantly turn on another physical machine and have everything configured and ready to go. So the databases were architected to be self-redundant with running copies of the databases on multiple servers. If you can in containers, I would highly recommend using a modern clustering database. You can't always do that if you're running legacy applications, or if your software development team doesn't really know how to use MongoDB or a document-oriented database like that, and want to run an classic SQL database, then you might have to. Then you're going to have to do some extra work to architect that. However, a big but here, for the vast majority of these use cases, you can use the container orchestration itself, the features built into Docker Swarm or Kubernetes, to solve a lot of problems for you. If your database dies, you've still got a volume running around with your data stored in it, so you can attach that to your container and restart your database very, very quickly. And in many cases, it comes back up before your monitoring even catches that it's even down. So trick with that is you want to use good storage. You want to use, you don't want to use just files on disk. you want to use an attachable storage system that's supported with good integration driver that you trust, and take advantage of the features that your storage engine gives you for operational capabilities. So part two of this, like we said, Docker certified Kubernetes storage, and basically vendors that want to test their drivers against Docker Enterprise 3 and known good tests. They're coming. Docker EE3 is not out yet. It will be out soon, and when that goes live, we'll be able to start certifying. Storage vendors against that. The big thing to be aware of with that is that most of these vendors are very interested in the container storage interface, CSI, which is a brand new specification, and they're not all entirely done writing all the code for that. So it may be a little bit of time after the EE3 release before all of the certifications are ready. But they'll work with your supported storage vendors and work with us. And if you have any specific requests, if you're a Docker EE customer, talk to your sales rep. They can work with me, or you can talk to me directly. My email address will be at the end of this talk, so that way we can get you sorted out. So third-party tool support, along with storage, third-party tool support helps fill in some gaps. You can use snapshots, which is a feature coming in the CSI interface later on, but you can out-of-band snapshot volumes as needed for data recovery. And there's also some other backup tools. We have certified backup systems that are partners of ours that you can also use for disaster recovery if you want to have belts and suspenders on your running databases. So the other thing that you want to be concerned with is know the limitations of your deployment and your architecture. So in this case, in the example that we're going to be running, we're running Docker EE3 on Amazon. So we're using EBS volumes as our attachable storage. One of the limitations there is that even in a common Amazon region, so we're using, in this case, we're using US West 2. There's 3 availability zones inside US West 2. The EBS volume only can be attached to Docker hosts, basically virtual machines that are running inside that particular availability zone. So you have to make sure that you have enough redundant hosts inside that availability zone so that you can fail over. These are just the kind of limitations that you have to understand with your architecture as you're deploying solutions on your container infrastructure. And most importantly, from the database itself, keep things flush to disk. So in the case of MySQL, which is the example that we're going to be using, we have in the container, we have sync bin logs set to true, which means that all the bin logs and all the bin logs are going to be written to disk as soon as the write commands come into MySQL. It'll flush that to disk. That way, if your database ever falls over, all your data is right there and it's easily recoverable. So let's take a look at a demo. What we're looking at here is we're looking at Docker Enterprise UCP. This is our admin panel, and in Kubernetes, as you can see, under storage, we have a storage class and a release persistent volume. I'll show you the storage class definition in just a second. And then under services, we basically got nothing running but the raw Kubernetes services. So let's take a look at the details of the database that we're going to run. So for the first thing, we're going to take a look at our service class. Take a look at our file. Storage class is what I called it. The storage class is a simple Kubernetes storage class definition. We have deployed Docker EE with the AWS EBS Kubernetes entry driver. So basically the native Kubernetes support for EBS. We've deployed that at deploy time. So all we have to do to create a storage class is this definition right here, just a YAML definition. And so we have done a kubectl apply with this particular YAML, and this is already running. So let's take a look at our database definition. There's two parts. This is a bit of a long thing, so we're going to scroll up and down a little bit. The first part is the definition for the MySQL database. It's just a Kubernetes service running with a pod definition with basically some setup information predefined. We've got a predefined database and an admin user and a root password of something very simple. In production, do not put your raw database passwords in your YAML definitions. Use Kubernetes secrets. But for this is just a temporary example. So I did this just to make it quick and easy to run. The other particular thing that you want to pay attention to is this persistent volume claim section. Again, in production, you want this to be a separate file. And I'll show you when we get done. When we clean up our environment, when I use kubectl delete and point it at the MySQL file definition YAML file here, it's also going to remove our PVC, which is going to remove our volume. And you don't ever want that in production. But again, just so I can do a one-step deployment here, we are setting this up in this way just to make it easy. So we're going to kubectl apply the MySQL.yaml, and this will come up relatively quickly. Takes just a few seconds. All right, so we have created a persistent volume claim, and the deployment and services are created. So let's take a look at the pod. I have to type it right. So we're going to do kubectl get pods to get the pod definition. All right, so we have MySQL-56 something or other. So we can do a kubectl describe, and I'm going to put this through watch so we can kind of watch it go. And one of the cool things is you don't actually have to type the entire name of the pod. You can just hit the first bit of it, and Kubernetes will do the right thing. So we have the pod is running. Everything's up and running, and we have our persistent volume. I didn't actually even need to do watch because it was already up by the time I typed it, which is very, very cool. So we're gonna cancel out of this. So again, this is just MySQL. We're not running a separate application that's talking to it yet. All we're worried about here is the database itself. So what we're gonna do here is connect to the database by running a separate container with a MySQL client using Kubernetes internal DNS to talk to the MySQL host. All right, so now we're talking to our database. And if we do show databases, you can see the DemoDB database that we created at runtime. All right, so what we're gonna do is we're just gonna write a table. We're just gonna create a table in there. Not even gonna write any line to this, but if we do a show tables, you can see we don't have any tables in the database. So we're just gonna create this table real quick. Okay, so let's redo show tables. All right, so now we have our tasks table that we created in this snippet. So what we're gonna do is quit out of this. Now, the tricky part is here, keep wanting to type MySQL. What we're gonna do is we're actually going to take a look at the pod here. And we're gonna find out which host our pod is running on. So if we scroll back up, we'll have this particular host here that's in our deployment. So what I'm going to do is I'm going to drain this particular host. So this ignore daemon sets flag. What that does is that tells kubectl drain that the native daemon sets that are managing Kubernetes and any of the pods that are flagged as a daemon set or labeled as a daemon set in Kube, let's not flush those because otherwise we completely lose that particular host from our Kubernetes install. And so Calico is our networking setup in Docker EE. So now we've evicted this particular pod from that node. So if we do another kubectl describe on the same pod, we should be able to scroll up and see, all right, now we're on an entirely different node. So we were on this IP 172.31.45.36. Again, we're running in US West 2 and Amazon. So we're now on a different host. So we have actually failed over this database almost instantly to a new node using the same database, using the same data. So what we're going to do is we're going to rerun that MySQL client, and we're going to confirm that our data is still there. So we're going to go into our DemoDB. Now, if you remember, we created this table live as we were showing this. So now we have seen that not only did we fail over, but our data is still there. And so this is, in production, this is all you really have to do. If you know and you trust your storage underneath, if you know and you trust your storage layer that's underneath your Docker EE and Kubernetes deployment, then we're in really good shape for showing for trusting that that we're good to go. So let's go back to the slides real quick. Couple points to consider as we move on. So always remember, flush your data to disk. There are a lot of databases will hold stuff in memory and will periodically flush that data to disk. That gives you a bunch of performance benefits for memory resident databases. The problem is that if the database falls over for whatever reason, then you don't retain your data. And knowing that these that container environments tend to be very dynamic, containers come up and go down at any given time. There's a lot more complicated things under the hood that can happen. So you want to trust that you have your data available at any given time. To preserve that data for disaster recovery, use out-of-band things right now, like snapshots, backup tools, and we have partners that do backup, that can do full backup recovery for your volumes. We also have a lot of storage partners that have snapshot features as well. Now the trick is right now is that you have to manage your snapshots out of band. There is no control underneath Kubernetes for snapshots yet. That's coming. The CSI interface from the Cloud Native Compute Foundation. It's a standard interface. Snapshot support is coming. They're actually in discussions on how to roll that out in CSI, and as soon as that rolls out, a lot of the storage vendors will be able to take advantage of those API calls. Not every storage interface is going to have snapshot capability. So if that's something that you want and something that you need, make sure that your storage vendors support that when that becomes available. I don't expect that. I don't expect that very soon, but it should be available. Ballpark, later on, late this year, early next year. I would expect. So, and again, that's not a Docker product. That is an upstream product, that upstream project that's going into Kubernetes. We don't have a lot of control over that. We do have folks contributing that are in the Kubernetes SIG storage community, but once that becomes available, we'll roll it into the next Docker release. So the persistent volume is bound to your persistent volume claim. Do not delete that unless you have a backup. Again, do not delete your persistent volume claim unless you have a backup if you need that data. As long as the PVC is alive, you should have your data available in your Kubernetes install. So remember, like we mentioned, this demo's example, keep your PVC YAML definition separate, so that if you ever do a kubectl delete and point it at your YAML definition file, that you know that you will be able to keep that data. Just a thing to consider. So for bigger databases, what if you need more than a simple database? So for the overwhelming majority of applications that you're running no more than a couple of gigs of database data. If dozens or hundreds of gigs, totally doable. in databases that are running in containers. When you start getting bigger than that, then you start having to do some funky things like sharding your data. When you have if your databases are very large, you're going to need to do some extra stuff. So first of all, for very large databases, use affinity labels in Kubernetes to define define where your containers are going to launch. Use scheduler hints to make sure that you can use scheduler hints to make sure that the database is running kind of isolated on its own host in your environment if you're running very, very large databases and containers. Sharded databases as well. You're going to be running multiple instances of the database, and they need a special handling and more engineering. You have to be able to make sure that your database, your service and pod definitions in your YAML files in Kubernetes are taken care of, as well as whatever the native conditions you have to do to launch all that has to be automated, fully written in to make sure that you can handle the shards as well. So what happens if you can't lose transactions? If this database absolutely positively can't lose a transaction no matter what? There's a couple of things that you're going to need to do. You can use a connection broker with running. You can run multiple copies of your database. If you're totally sharing it, if you're running a clustered MySQL or a cluster database that doesn't do master slave, use a connection broker as an additional container, or in-app library depending on your deployment of software languages and whatnot. Java applications tend to use a Java connection broker that's built into your application itself. Cluster your database, whether it's master slave, full horizontal scale clustering, do that as well. Again, it requires more special engineering and more special handling when you're doing that. And using service discovery host names. So when you like just now, we're using the MySQL host name under the default namespace in Kubernetes to be able to access that database. You can use service discovery to be able to handle connections to round robin to all of the databases in your cluster if you need to. And again, like using sharded databases, use node affinity rules to make sure that you're not running multiple instances of that database on the same node. That way, if you do have a failure, if you do have a physical hardware failure on the node, then you don't lose a bunch of database instances on that one node. So those are kind of the ballpark ideas of what you can do for bigger databases. Work with your application engineers and your database engineers to make sure that these things stay up and running. But again, the overwhelming majority of applications that are hosted are much smaller databases, and they're a lot easier to deal with as singletons, just with the trusted volume running underneath. So that's basically the talk. That's the demo. Now we have time for questions. So we're going to start going over that in just a second. Thank you.
Hi, thank you very much, Keith. So as Keith said, we are going to start into our Q&A session right now. So Keith, if you could take a moment and look over there in the questions panel and see if we have any new questions coming in, or if you want to review some of the questions that came in during the presentation, and see if there's any that you want to call out. While Keith's doing that, just to remind everyone, if you haven't submitted a question and you do have one, you can do so by posting your questions in the questions panel over there. And we do have Keith that will grab some of those. So yep, Keith, I'll go ahead and turn that over to you if you want to call out some of those questions now.
Absolutely. There's most of the questions that came in we've been able to cover pretty easily via just the chat, but there's a couple of really good ones that I want to highlight. One of them is asking if the persistent volume claim is it will enforce single access of the volume. That's absolutely, it absolutely will. So when your storage administrators and the folks that are running Kubernetes create your storage class, that's actually a standard field that they'll need to put into the storage class. So it's not done on a volume basis, but it is done on a storage class basis. So typically, almost everything is kube will enforce single mount, so that you can one container can mount the same persistent volume at the same time. The only time you'll see multiple access like that typically is unless you've got a really interesting hardware storage setup, is if you're using something like NFS or some type of network attached storage. In those cases, in those cases you normally can have multiple containers talking to the same volume at the same time, but you really don't want to run databases on that and all writing database files to the same location, because clobbering is an absolute thing. Somebody asked if flushing data to disk can be harmful to your database performance. It can be, absolutely. But if you're going to be using a singleton database container to write data, if you're comfortable with data loss, you absolutely don't have to sync. You don't have to sync your bin logs and stuff. But if you have any intolerance for data loss, then go ahead and take the performance hit. So we got some new questions coming in as well. Question is, are databases deployed as stateful sets? Yes, you generally deploy databases as stateful sets. And in fact, in the demo, that's what we did. The stateful set in Kubernetes is just a way to, it's basically a wrapper for the pod itself, and it tells Kubernetes make sure that the containers in the pod that you defined in that pod are always running. So it'll basically maintain state for the containers that are running in that pod. Second question is, what's the difference between a Docker container and a VM? That's a pretty big topic, but fundamentally a VM is emulating an entire computer. So you have a kernel specifically running for that virtual machine, and you'll have a hardware emulation layer between the actual hardware and the VM, to where basically everything it looks just like a physical server, which for the processes running inside. A container is a single process that is running underneath a container management system, and has shared access to the resources of the hardware. So the advantage is that you can stack them a lot tighter. You can have a bunch more containers running on one host, because you're not having to duplicate processor time and processor cycles and memory pages for kernel space and all that kind of stuff. And they're also typically the container images are a lot smaller, a lot more easier to replicate, but it's a much bigger topic. That's actually a totally separate talk. So the storage options for Windows 2016 containers, that's a very good question. The storage options there are actually kind of limited. You can basically you can use native on disk storage. Also, be aware that Kubernetes is not supported on Windows yet. It's going to be soon. We're working with Microsoft to make sure that support happens, and it'll probably be Windows Server 2019 when we roll out Kubernetes support. It'll be rolled out for 2019. And once it rolls out for Windows Server 2019, you'll have, on the outset, you'll have basically most of the entry drivers should work, and external provisioners should probably work, and CSI will take a little bit more work and probably won't happen at rollout, but you'll be able to. That's when we're gonna patch in flex volume support for Windows hosts. So, but as far as currently sits for Windows Server 2016, use Docker volume drivers, for external support, and natively you've got support for basically anything you can plug into the box physically. if you're running on Windows Server 2016 container hosts on top of a VMware system, you can also use the VMware storage layer as a middleman to make it a lot easier to deal with. How do you handle pod replication? Would you have multiple PVCs, and how does the data will be synced by between the PVCs? Typically, you have one PVC per database instance. So if you're running a cluster database, or if you're running multiple database nodes in your deployment, you'll have one PVC attached to each individual node. And so each individual database container. So when that database container gets rescheduled, if it falls over for whatever reason, or if the container host is being taken offline for service or whatever, the PVC will follow that individual container in your pod. And again, you'll want to run a stateful set to wrap around that to make sure that everything stays alive. But yeah, that's how you do that. It just depends on, some of it also depends on the database you're running. So you kind of have to architect your pod and your container architecture to make sure that you're fitting the needs of the specific database as well. So the next question, since databases have OS level optimizations, the database pods are always scheduled on the same node as part of the stateful set functionality. They do not always have to be scheduled on the same node. Databases, so you can provide scheduler hints to Kubernetes or to Docker Swarm to make sure that a particular database container lives on the type of node that you want it to. But in general, if it's a Linux container, it's going to live on a Linux container host. If it's a Windows container, it's going to live on a Windows container host, and the orchestrator will just figure it out from there. But if you have specific needs, if you've got like specialized container hosts that you want to run databases on, then you'll need to add labels to them. And then you can, using scheduler hints, you can tell Kubernetes or Docker Swarm, hey, launch it on nodes with that label. That does require a little bit more knowledge of your infrastructure, but honestly, if you're starting to run anything more than a singleton database, like we demoed, you're gonna have to architect it for the specific container infrastructure that you're running on. So you'll need to know a little bit more of the implementation specifics anyway. I mentioned swarm and passing. It doesn't use persistent volumes, persistent volume claims. The person asking the question says that they use NetApp as NFS storage. Any problems using a database container connected to NFS with Swarm? Not really. You can use this exact same pattern, just a singleton database in your compose file with an attached volume. It works just fine. It's basically the exact same pattern. The only problem with using NFS is you want to make sure in network attached storage tends to have higher latency, and if you're pushing a whole lot of data through that, you might run into some issues. So I would definitely recommend using block storage for your databases as opposed to file storage. And with NetApp, you actually can do both. You can just set up a second Docker volume driver to talk to your NetApp systems in block mode, and you should be able to do that just fine, actually. But you can run it on NFS. For lower volume databases, it should work just fine. So resources link where you can try out the Kubernetes deployment and storage stuff. Not easily. You can try out some Kubernetes deployments with some of the online Kubernetes examples. The actual deployment that I used was basically the Kubernetes database tutorial. I took the pod definition directly from there, and really didn't change it much at all. So So you can actually use that. The big thing there is you want to be able to do a failover and to play with that type of stuff. You're going to want to be able to work with a Kubernetes install that has multiple nodes, and most of the online free easy to access ones don't have that. One thing you can do, so the Docker Enterprise Public Beta just went live today, I think, or yesterday. So the EE3 beta, you can sign up for that and start kicking the tires on it, and you can deploy that on Amazon or Azure or any cloud that you want to use. There are native cloud drivers for both. And that's probably, if you want to actually play with failover and that type of thing, I would recommend doing that. So any more questions that we have right now, guys? Give it just a little bit more time for folks to come up with questions, and if not, we can wrap up.
Okay, again, if you have that question, pop it on over into the questions panel in the window there. As he said, we'll give another few seconds to see if any new questions come in before wrapping up today. Okay, and I'm not seeing any new ones coming in. So I will go ahead and conclude the webinar. Thank you, Keith Hutchins, and thank all of you for the great questions today. We appreciate you being interactive with us. Just another reminder that today's session was recorded, and you will receive a follow-up email to view the recording in the next few days. And we thank you again for your time today and joining us. We hope to see you next time. Have a terrific day.
Thanks, everybody.